The objective of this video is to introduce the Maxwell stress tensor for magnetic force and torque calculations. But before we get there, I want to frame this within the broader context of this course and how we will be using the Maxwell stress tensor. This is another analysis tool. However, this analysis tool assumes that you already have calculated your magnetic fields everywhere in the cross-section of your machine. So if we zoom out here, we can see that we have a problem statement. In our case, our problem statement is an electric machine cross-section. So we're told that we have an electric machine. We're given the geometry, what its excitation is, that is, whether there's permanent magnets, whether there's coils, how much current is in the coils, and what the rotor position is. And we want to use that geometry, we want to take that geometry and figure out how much force or torque is acting upon our rotor. And so our first step is that we take the geometry and then we calculate the fields. And we do this using either finite element analysis or one of the analytic techniques that we've been talking about, such as magnetic equivalent circuits or a direct solution. So we use our calculation technique and we get the fields in the cross-section of our machine. And once we have the fields in the cross-section of our machine, we then use a calculation method to determine the forces that are acting upon our rotor. And so if we're using this in an optimization problem, we have a candidate design or a problem statement on the left side, and then we use our toolbox, the tools in our toolbox, to calculate a certain performance variable based on the force or the torque that's acting on our rotor. And we do this by first employing a field calculation technique, and then second, employing a force calculation technique with knowledge of the fields. And so that force calculation technique can either be the Maxwell stress tensor, like we're going to be talking about now, or it can be something else, such as virtual work, or another technique that's inspired by the Maxwell stress tensor or the virtual work method. All of these methods stem from the same physics. So make no mistake, we have the same governing equations at play, which is the Lorentz force law and Maxwell's equations, but how you formulate it has certain advantages for your calculation method. It may require a different number of evaluations of your rotor position, or it might have different numeric stability properties in your FEA solution. For our analytic calculations in this class, we're going to use the Maxwell stress tensor a lot. And then you'll see that when you use your FEA code, there's a modified approach that's used because the Maxwell stress tensor is prone to numerical problems that result from our FEA mesh discretization. And you'll be reading about that in the manual for your FEA tool. So let's talk about the Maxwell stress tensor. What is it and how do we use it? So as I mentioned, all these techniques come from the same fundamental governing equations. If you open up a Fields book, you can find a derivation of the Maxwell stress tensor that starts from the Lorentz force law and employs Maxwell's equations to write the force law in terms of only fields. And the result of doing that is a very complicated set of equations. So we introduce a tensor or tensor notation in order to express this as a single equation. And so a tensor is denoted as a vector with an arrow going both ways. And you don't need to worry about memorizing this. We're not going to be using the tensor notation in this class. This is merely giving you the background of where this comes from. And so you'll see by the end of this lecture, we'll have a compact set of equations that apply only to torque and forces produced on an electric machine's shaft. So the result of using Maxwell's equations in the Lorentz force law is that you get a single equation that looks like this. And in this equation, you see that we've got subscripts I and j, and that's because the tensor is a matrix, and a vector is just a column vector or a row vector. It has just a set of quantities. If it's a vector in xyz space, it has an x and a y and a z quantity, whereas a tensor in xyz space would have a matrix of 3 by 3, an xx component, an xy component, an xz component, a YY component, and so on. And the next thing to note here is that we've written our tensor in terms of both E and B. B is our magnetic field, of course, and E is our electric field. And in our class, we're not worried about the electric field. We're assuming it's 0 everywhere, so several of these terms drop out. The remaining terms depend on, again, B with the subscript of I or J, which are the components of the vector B, as well as the magnitude of our field. These subscripts I and J that denote the entries in the matrix of our tensor or the vector of our magnetic field relate to the coordinates that we are using. This can be any orthogonal set of coordinates. It can be the XYZ coordinates, it can be cylindrical coordinates, it can be spherical coordinates. We'll find it most useful to use either Cartesian XYZ coordinates or cylindrical coordinates in our class. The next item to discuss in this equation is the Kronecker delta. That's this variable right here, this delta with a subscript of I, j. And that's referred to as a Kronecker delta, and it's a special function that is 1 only if I is equal to j. And it's 0 if I and j are not equal. So in other words, that's just a way of saying that this entire term over here disappears if you're talking about two different coordinates. If you're talking about I equals x and j equals y, that term is 0. But if you're talking about I equals x and j equals x, then that term is -1/2 magnitude of b squared. And so far we've talked about how to interpret this equation above, what I and j mean and what delta ij means, the Kronecker delta. Now let's get into how this can be used to calculate forces. This is set up so that you can calculate force by integrating the following function over a volume. And for us, this partial s, partial t is 0. This is the Poynting vector, and for our class of problems, we assume that it does not vary with time. So we're left with just this term here. And if we use the gradient theorem, we can rewrite this as the integral of the tensor over a closed surface. And that closed surface is the surface that you wish to calculate forces upon. So, for example, if you were to consider a cube in space, and you want to know what forces are acting on that cube, you can integrate the Maxwell stress tensor over all surfaces of that cube. And the way you interpret this is that a tensor dotted with a vector can be expressed like this, which is to say that it's a summation of the tensor integrated over each of the surfaces of your volume. And without going into too much more depth than this, I just want to get to the punchline, which is that this allows us to interpret the components of our Maxwell stress tensor as a force density in direction I and acting on surface j. And so because of this, we can say that if I equals j, so for example, txx or tyy or tzz, these are pressures. That means that we have a force acting in the same direction as our surface, and that's just a normal force pressure. Whereas if I is not equal to j, if we're talking about x, y, yz, and so on, these are shears. These are creating torques. These are shears on the surface. We can summarize this as saying that we can go from our Lorentz force law, which is in terms of a point charge, electric field, a magnetic field, and a velocity, and we can convert that to an expression that gives us force, pressure, and shears in terms of the electric and magnetic field. And simplifying that for our case, where we have no electric field, and we know that our Poynting vector does not vary with time, we end up with a rather simple expression for the force density, for the stress that's acting on the surface of a volume that we want to calculate the total force. So if we integrate that stress, we can get a net force or a net torque on that surface. So that's the theoretical background for the Maxwell stress tensor. This is a rather mathematical discussion so far. Let's make it practical. Let's talk about how we will use it for electric motors. And you'll see that it becomes a very useful tool for calculating the force or torques on our motor shaft. And so what I've drawn here is a shaft with the axial direction aligned along the z-axis, and then I've labeled a cylindrical coordinate system. I've labeled our unit vectors as z hat for the axial direction, r hat for the radial direction, and phi hat for the circumferential direction. We're not going to be talking about vectors in this form much in this class, and in fact usually when we talk about angles we'll be talking about the angle alpha in the class, and a lot of our nomenclature will have a word of tan for tangential in the subscript of a quantity that's talking about something in the circumferential direction or along the direction of our angle alpha. And in the radial direction, we'll oftentimes use a subscript of n for normal, the normal direction or the radial direction. Okay, so for motors, we're considering cylinders. And sometimes we'll be considering this in Cartesian coordinates because we'll unroll our motor. We'll take the rotary motor and we'll unroll it to be a linear machine to make drawings easier, to make math a little easier, to illustrate points. But in this case, let's talk about it being a cylinder. And we are primarily interested in forces that are acting on the radial surface of the cylinder. So we want to know what forces are acting on this radial surface, and we're going to assume that our fields are only in the radial or normal and tangential direction, that we've got no axial component. That's the 2D assumptions we've been talking about. And so that means that we're interested in the components of the Maxwell stress tensor that are referred to as TRR, that is forces that are acting in the radial direction and on the radial surface, and T phi r, that is forces that are acting in the tangential direction but on the radial surface. And we'll be referring to these as sigma Fn, so a force density in the normal direction, and sigma F tan, a force density in the tangential direction. So what we want to do now is we want to calculate expressions for sigma Fn and sigma F tan, that is TRR and T phi r. And so to do that, we'll go back to our Maxwell stress tensor expression up here, and we'll plug in values for our magnetic field to get the expressions that we desire. So we want to have TRR and T phi r. And for our first expression, sigma Fn, that's the force density in the normal direction or the radial force density, we plug in I is equal to n, or I is equal to the radial direction, and j is equal to the radial direction, and we get this expression directly from our Maxwell stress tensor equation. Now we can note that b, the magnitude squared, is equal to the normal component squared plus the tangential component squared. And we finally arrive at this expression. So that is our normal stress. That's the stress acting on the surface of our rotor in the radial direction. We'll now calculate it acting in the tangential direction. And we get this expression, where we note that our Kronecker delta is 0, so we only have the first term in this case for our magnetic fields. So we can summarize this in a vector form. And we end up with this final set of expressions. The bottom row, sigma F tan, is our shear. These are the forces that are pulling our rotor around. This is what creates torque. And our top term is the radial force density, or the normal force density, and this is what creates unbalanced forces that our bearings try to oppose. So these are forces that tend to pull our rotor towards our stator. And ideally, if you've got a good winding layout, if you've got good machining, good design, your unbalanced forces are 0 when your rotor is centered. Unless, of course, you're designing a bearingless motor where you actually intentionally create unbalanced forces to support the motor like a magnetic bearing. So we can use these expressions to calculate the net torque and force on our shaft. Let's consider an example motor. In this case, I've drawn a slotless stator and then a permanent magnet rotor. we want to know how to calculate the total torque acting on our rotor and the total force. Let's start with torque. We're going to integrate sigma F tan on the surface of our rotor to find torque. And again, remember that BZ is assumed to be 0, which means that there's no forces acting on the axial ends of our rotor. So we'll just integrate sigma F tan over the radial surface of our rotor. And remember that our motor extends into the page some axial length L, but since we're not worried about the axial magnetic field, we can just assume that we have the same force density acting on the rotor in any given cross section. So as you travel the length of the rotor, your force density is always the same. But of course, your force density varies as you go circumferentially around your rotor. As you vary alpha from 0 to 2 pi, your force density is going to change. So we'll assume that our rotor has a radius r. I've indicated that below. And then we're going to have this angle alpha that we're integrating our force on, is this angle coming up from the x-axis going around counterclockwise. So torque is equal to force times the length of the lever arm that force is acting upon. And in that case, that lever arm is just the radius of the cylinder that we're integrating. So we're going to have torque is equal to r times the integral of sigma F tan. So that's going to be the integral of sigma F tan on the surface of our rotor. And again, I commented that we have the same force density at any axial location. So our axial length is just going to come outside of this integral. And we're going to be left integrating over alpha from 0 to 2 pi. And we can express our differential length in terms of differential alpha, noting that if we have the surface with a radius of r and a differential angle of alpha, this length right here is equal to r d alpha. And so that's just how you set up your volume integral or your surface integral. This goes back to your vector calculus days. And if you evaluate this expression, you'll get the total torque that's acting on the surface of your rotor. Or you'll get the total torque that's acting on your rotor by integrating the shear stress density. And I'm sure you can imagine we can do a similar thing to calculate the total forces acting on our shaft in the x and y direction. So that's the level of depth that I want to leave it at this point. So now you know how to calculate, in principle, you know how to calculate your total torque and force acting on the shaft of the motor if you are given the magnetic fields that are in the air gap of your machine. In summary, we've introduced the Maxwell stress tensor, and we've talked about how this fits within the broader context of our course, how we go from being given an AC machine, we can use techniques to calculate the magnetic fields in the cross-section of the machine, and then use those fields to calculate the force or torque that is acting on the rotor. We developed the Maxwell stress tensor to be used for these calculations, and we provided some background on where the stress tensor comes from and how it fits into Maxwell's equations. And then we've shown how this can be applied to a motor. And we've left it off with some rather simple expressions for the shear and pressure forces that are acting on the surfaces of our rotor in terms of the magnetic field components.